Hello, welcome to our first part of our four-part video series, and in part A, we are going to be dealing with two tanks in series that have equal cross-sectional areas of 2 meters squared, draining through holes at their bottom, resulting in flow rates from each tank equal to 2 times the initial height, square root of the initial height. The first tank has two inlet flows coming in, so we've got U1 and U2, with the flow rates of 2 and 0.5 meters cubed per second respectively. And then the second tank has, in addition to the flow coming in from the first tank, an additional flow, which we're going to call U3, coming in at 0.4 meters cubed per second. And so we're going to first start this video by calculating the initial steady state height of levels in the tank. And what we're going to be moving forward with in this is we're wanting to assess the Jacobian method versus the solve IVP method, and compare the two. But really, we're wanting to explore the Jacobian method here because we want to be able to assess how our functions are going to be changing with respect to different independent variables. And so we've got our flows coming in, our system inputs, and we want to be able to assess how are the different functions within our system changing with respect to our various inputs. And so, for example, how is the fluid height in the tanks going to be changing with respect to both the different flows coming in, with respect to each other, and with respect to just the flows coming into each tank and the inputs themselves. And so that's where we're going to go ahead and start by kicking off here. So let's sketch out what we just read. And so we have one tank, tank 1, and we've got our H1. And as we noted, we have one stream coming in, U1, another stream coming in, U2, and not the band. And that was corny. It just popped in my head though. This is the flow rate leaving the tank, and we're differentiating between, even though these are both volumetric flows, the U's are signifying our system inputs, things that we're changing irrespective of where they're not impacted by what's actually happening in the system, whereas the Q is impacted by what is coming into the system and by the system dynamics itself. And so that's the reason for the variable differentiation there. Tank 2 has its height, its fluid height. And so not only does it have Q1 coming in, but it also has its own independent input, system input coming in as U3, and then leaving would be Q2. Now, these are going to be equal to the cross-sectional area times the square root of 2g, here's h1, and this one is going to be 2gh2. And here is going to be our alpha equaling our cross-sectional area, basically everything that we have right here. Now, we want to go ahead and move forward, so we're going to go ahead and set up each of our differential equations with respect to, in this case, we're going to be evaluating, we want to first assess what are the initial heights in each tank at steady state. So let's go ahead and say our cross-sectional area times the difference of fluid and height in tank 1 over time, and that's going to be equal, well, what's coming in versus what's leaving. And then here for Q2, not Q2, but H2, we've got the fluid in tank 2, the fluid level is changing with respect to time from what's coming in minus what is leaving the tank. So we're going to go ahead and move forward, and we're going to set this up in terms of just a Jacobian method, because what we want to do is, right now we're going to have nonlinear functions, and we want to be able to linearize it. And so we need the initial steady state fluid levels of our tanks so that we can have our specific parameters by which we can then use the Taylor series expansion through the Jacobian method in order to linearize our functions here. And so let's go ahead and begin doing that now. So we need to bring in our tools. All right, bring in the various tools that we're going to need. All right, and then we're going to need this. And then we are going to use a root solver in order to determine what our initial heights are in both tanks. So let's go ahead and bring in from that tool, from SciPy. All right. I think my connection might be a little bit slow here. So now let's go ahead and start bringing in our parameters that we just drew out. So we're going to set an alpha as 2 so that our fluid levels aren't too high. Cross-sectional area was said to have been 2 meters squared. And then we're going to define our right-hand side, which we have our time, our height, and so the height is going to be what we're going to be evaluating as our functions, and then those respect to the system inputs, which is our u. All right, so our h1 and h2 is going to be equal to h. u1, u2, u3, we're going to bring those as u. Now q1, what did we say q1 was? Q1 was alpha times h1, if we're doing q1 here, the square root of h1 there. Okay, then q2, same thing, except for the fluid level in tank 2. All right, now we're going to return, and we're doing it as a Jacobian array. And what do we have? Well, we have our two functions. And the two functions that we're evaluating are the fluid levels in both tanks, tank 1, tank 2, at the steady state conditions. And what did we say? That was, okay, 1 plus u2 minus what we say q1 divided by AC, and then we said q1 plus u3 minus q2 divided by AC. So in order to bring in, so we want to do the root solver here because we want to figure out what are the initial fluid heights in both tanks. So we're going to call this variable h initial, and we're going to do our root using our lambda tool. And it's regarding our right-hand equation that we just defined above. Well, time, it's not with respect to, it's just this regardless of any time. It's at steady state conditions here. Our height is going to be, what we're going to call that our x, because that's our function that we're evaluating here. And then u is going to be what are the initial u flows coming in, the initial inputs to our system. And we haven't defined u initial yet, so we'll go back and do that in just a second here. We need to provide a guess, and we want it in terms of x to be kicked out as our value. So let's go ahead and define u initial now, which is equal to an array of values. What did we say they were again? 2, 5, and 4. To 0.5, I should say. 0.5 and 0.4. Okay, let's rerun that. And let's run that. Okay, now let's figure out here what our values are. Okay, so it is telling us that at steady state conditions, our fluid level in our first tank is 1.5625 meters high, and then our second tank 2.1025 meters high. And so those are steady state conditions. It makes sense that the second one would be a little bit higher. It's got just the flow from the first, and then the third stream coming in, and so it evens out at a little bit of a higher level. And so now we're going to move on to assessing the next portion. All right, so now in our second part of this video, we are wanting to use JAX to linearize the dynamical equations with respect to the dependent output variables h1 and h2, and also with respect to the input variables u1, u2, and u3. And so what we're doing here is we're looking at the state space model that we have here, and in this case we're dealing with a continuous time invariant model. And so in the state space, we can evaluate as many different things as we want with our functions and how the functions are changing with our deviation variables. In this case, we're wanting to look at a couple things here. One is how is this function, and in this case we're going to be evaluating how is this function changing with the fluid heights in both tank 1 and in tank 2. And then how is this function change? What is the state of our system? And how does this function change with respect to the height in H1 and H2? So as the fluid heights in our system change, what impact does that have on both of our functions? And so that is what we're going to do here with unpacking our Jacobian method here and linearizing using our Taylor series expansion. And so we're going to need to give it the specified values, in which case we found our initial height, we've given our initial flows, and so that allows us to move forward with our Jacobian here and seeing how the functions change and how with the fluid heights, and in this case we're going to be dealing with fluid heights, but also with how do the functions change with any change in our system inputs with our flows. So let's go ahead and bring this in now. So we're going to call it, since we're dealing with the fluid height first, let's call that JH. And that is going to be our JAX Jacobian. And our right-hand side now, we have three options. We're not looking at how our functions are changing with respect to time. We're going to start with seeing how do our functions change with respect to fluid height in our tank. So that is going to give us it's going to evaluate our functions with respect to the fluid heights that are changing. And then we're going to say JH equals our JH function that we just said. Now we need to give it the values in which we want to linearize our Taylor series expansion upon. And so we've got, we're not concerned with the time here. We are wanting to evaluate it at the steady state height of our fluid levels in the tanks, and then our initial flows, our system inputs that were coming into the tanks. So let's go ahead and do that here, run that. All right, now let's see what that gives us here. So these values that it's kicking out, it's giving us our matrix of values. And so this first value right here is assessing how does this function change with respect to height, the fluid height in tank 1. And then this value right here is saying how does this function change with respect to the fluid height in tank 2. And of course, I'll pull this back up. That would make sense. Shoot. Oh. There we go. Once it loads here. Well, when it chooses to load, it makes sense that we would be getting a 0 for this. Should be giving a 0 here for height in tank 2. Why? Well, because if we look at our model here, the fluid in tank 1, the function at which our fluid height is changing, it doesn't care about what's happening in tank 2. The tank 2 could be overflowing for all we care. That's not going to have any impact on the fluid height in tank 1, and that is indeed what we see here. But tank 2, on the other hand, is impacted by both the fluid height in tank 1 and the fluid height in tank 2. And so we see here our function in tank 2 is impacted here by the height in tank 1, and it's also impacted here by the fluid height in tank 2. And so that is what we're doing here. So now the next one that we're going to assess is how do our functions change with respect to our system inputs, our u's here. All right, so now we're doing pretty much the same thing, except now instead of assessing how do our functions change with respect to the fluid heights and how those are shifting and ever changing, now we're going to be assessing how do our functions change with respect to our system inputs. And so that's why we're going to call it JU here. So our JU function, again, we're going to do our Jacobian, but now in this case, we're not evaluating it at fluid heights, we're evaluating it at our system inputs. And so if we go up here, our right-hand side, our third input in our right-hand side that we've defined here is indeed the system inputs and the flows there. So that's why we're going to define it as 2 here. And then JU equals our JU function that we just defined above. And then again, we're not with respect to time, but we are evaluating initially with the initial fluid heights at steady state, and then our initial system input values. There we go. So now, if we run this, what we're going to see here, and what we should see here, is that our first function is only impacted by, should only be impacted by these system inputs, because of course here U3 doesn't enter tank 1 at all, so it shouldn't have any bearings on our first function. And then so let's go ahead and see if that is the case here. And sure enough, we see that U1 and U2 are indeed impacting our first function, but U3 has no bearing on it. And we do see the opposite, which is that U3 is the only thing that would be impacting as U3 changes. This is the bearing that it has on our second function, which is what we'd anticipate seeing. So now we're going to go ahead and move forward with the third part of our video here, in which we're going to be looking at from what we just set up just now. We're going to be looking using SciPy signal state space, and so we want to obtain a linear time invariant representation of the system. So we're going to set up our state space C and D matrices to isolate H2 as the only observed variable. And so as we just were looking at our state space, we can assess as many or as few inputs and deviation variables as we desire. And in this case, we're going to just lock in and focus in on H2. Okay, so basically what we're trying to do with this is we want to show our state space conditions in order to obtain our linear time invariant, our LTI representation of the system. And what we're going to do here is we're going to isolate it at where we're seeing H2 as our only observed variable. And so before we were assessing how functions change with respect to the deviation variables, and here we're just looking at a single variable, not a function, but just a variable in and of itself with the fluid height in tank 2. Now, we also need to be able to, for a state space system, we have our A and our B for matrices, which was our Jacobian with respect to fluid height, and then Jacobian with respect to fluid inputs to our system. Now we need to figure out our state space C and D matrices in order to proceed with our overall state space representation in our system here. So let's go ahead and bring that in now. And so first, before we do anything, we have to bring in our tool, which is our SciPy signal. We're going to call it sig. We run that. Okay. Now just a little cue in on what we're going to do here in isolating our variable. Let's go to another page. Is we're going to say, so H2 is what we're wanting to define here for y. And now, so if we have our H1, we have our H2 for both of our tanks. So how do we go about isolating tank 2, the height in tank 2? Well, we're just going to say 0, 1 for our matrices. And then we have the other thing we have in our coming into our system as a deviation variable is our U1, our U2, and our U3. And because we're trying to set things where we're isolating only with respect to H2, we're going to just forego all these. We don't want to look at our system inputs or our H1. We're just isolating our focus in on H2, and so that's why we're going to only pick using this matrices setup that we've just shown. So let's go ahead and we'll call it LTI system, and that is going to be our state space. Now with our state space, what state space requires is our A, B, C, and D for our matrix, and so our A is our JH that we defined above, our B is our JU that we just defined above. Now our C is what we just showed, what we just wrote out, which is we're isolating H1, and we're only looking at H2 here. And then again, the D in our system would be all of our system inputs, but we want to isolate those as well. So let's go ahead and isolate those now. And there we go. So now, if we type in our variable that we just named, this is our state space conditions. And so now we're going to be able to proceed by doing transfer functions in with regards to what we just defined here and showed as our state space conditions. All right, so now that we have our state space conditions, we need to convert this into a transfer function, because what we want to be able to show here is how is, in this case, what is the transfer function between H2 and U3. And so we've isolated everything up to this point in terms of looking at H2. So we're zoning in on how does H2 change. Now what we're wanting to set up is what is the transfer function between H2 and U3. So as our system input U3 changes, what impact does that have on H2? And so that's that impact. What is that impact? That is our transfer function. And so the amount, the degree, the sensitivity, however we want to put it, of which U3, any changes to our input, our system input of U3, whatever amount that impacts H2, that's our transfer function. And so that's what we want to look at here. And let's go ahead and write out what we're working towards and then code it. And so our H2, upon doing the Laplace transform, is it's going to be impacted. I'm making a box, and each box here is a specific transfer function multiplied by our system inputs that would be having a bearing on the height of tank 2. And so here we've got U1, U2, and U3. And in this case, we are just going to be focusing in on U3. And so it's going to end up producing a polynomial that looks like this. So we've got this right here for a numerator set of values. And then we've got this here for a denominator. And we've got this. And then we've got this here for a denominator set of values. So let's go ahead and figure out what these values are. So we need to determine the coefficients in both our numerator and in our denominator. And that's going to then give us this is right here our transfer function. That's going to show us the sensitivity to which U3 impacts the height, the fluid height in tank 2. All right, so we need to convert our state space into being able to be used in a transfer function. And so we need to set that up here, sig, and so it's our state space to transfer function is the tool we're using here. And this requires our A, as we can see here, A, B, C, and D matrices, which is everything that we've defined right here. So let's go ahead and copy and paste this. Probably give me one too many parentheses in it. There we go. Okay. And let's go ahead and, oh yes, okay, so it defaults to the input that it's evaluating is 0, meaning our U1. So we've got U1, U2, and U3. Those are our 3 system inputs. So let's go ahead and specify this as what we're doing is H2 with respect to H3. And so what this is showing here is this is our numerator. And so this is how, these are the coefficients for our numerator for the polynomial equation that we set up here. So our A, B, and C, A, B, and C, or N1, N2, N3. D1, D2, and D3 is how we've written it here. And then in our denominator, right, so D1, D2, D3. Let's go ahead and name this. We're going to, and then we are also going to specify this as a variable. So H2 to U3 transfer function, and this is transfer function numerator denominator. All right. So now these are the coefficients, and so let's go ahead and write this in here. So we've got 0.5 and 0.2 for the numerator. So this equals, obviously the 0 cancels out the s squared. What do we say? 0.5s plus 0.2. And then what do we have here? 1, and then 0. Let's say 745. Well, don't need to write the 1. Plus 0.745s. And then 0.138. And this, so right here, what this is saying is this is our transfer function, and this is the degree, the sensitivity to which U3 impacts any changes upon H2. So U3 is independent. We can control that. We can manipulate that as much as we want by increasing or decreasing the amount of U3, and the degree to which U3 impacts H2 is shown by our transfer function right there. So the last thing we want to do in this first video is we want to calculate the step response of the linearized model that we just made, and compare that against the solve IVP method, which we've done in the past with the original nonlinear model. So we're basically comparing the new linearized model that we formed through the Jacobian method, through the Taylor series expansion, with the initial fluid heights that we gave it and the initial system inputs that we made it. So we linearized our model. We're going to now compare that with the nonlinear model through solve IVP and just contrast the two against each other. And so let's go ahead and do that now, which means we're going to need to import plotly.subplots, or should I say from plotly.subplots import make subplots, and then from scipy.integrate import solve IVP, because these are the two methods that we're going to be using now, the newest tools in our tool belt. All right, so we're generating a step response. Now what we're doing here is we're asking, how does the fluid height in tank 2 change via the transfer function? Will change via system input U3, and that's shown by the transfer function, the sensitivity of it, and how does that change over time. And so we're going to say H2, we're going to call it deviation, and this is equal to the step response over time. So U3 TF is what we called it, step. Okay, so now we're going to go ahead and subplots. All right, so our X variable is our time. Our Y variable is our step response. Our Y variable is how does our H2, the height in tank 2, deviate over time. And so we do have our initial fluid level in tank 2 that we need to take into consideration. So 1 and not 0, because we're dealing with tank 2 here. And let's go ahead and update our layout. Give it a width of 800, height of 600, type, and template. There we go. What is it now like? Fig, make subplots. Here we go, I just forgot the parentheses. Okay, so this is how our fluid in tank 2 changes with any responses to U3 over the course of time. And so now let's go ahead and compare that and contrast it with our solve IVP, which solves directly for nonlinear models. All right, so now let's go ahead and bring in our solve IVP to show and display our nonlinear model, and then compare and contrast that against our linear model that we just did. So our solve IVP tool, right, our right hand side, we've got our T, we've got our H, and then we've got our system inputs. So we've got our initial, and then we're only considering and focusing in on U3 here. Now our time span, let's go ahead and say 0 to 20. Our H initial, which we're looking at in our tank 2. And then the method we're going to use for solving. And then we need to kick out a particular we need each solution, each point that gets calculated to be able to be evaluated at each point. And I think I've got one too many parentheses, it looks like. No, I don't. I think we're good. Doesn't like that. What don't you like? That one's fine. Okay, there we go. So now let's go ahead and name this as our results. Okay. Now we're going to go ahead and we need to plot this out. So we're going to have our NP lin space because we want to plot this out evenly. And then we want H1 and H2 to be evaluated. And these are going to be evaluated along, we want the results from our time plot. H1, H2 are not defined. Sol is not defined. Well, that's because I just need to flip them the other way around. Okay, there we go. So now let's go ahead and plot this out. Let's copy a lot of what we've already typed so we can compare and contrast. All right, so this is our first initial one. We'll give this the name of linear, so we can just compare the two. And then add this in again. This one is called time plot. And this one we've called, oh, whoa. Here, we're just focusing in on our tank 2. And this one we're going to go ahead and call non-linear. And, oops. Let's try this out here. Okay. Okay, so look at this here. So here is our non-linear, and it's getting us up to 3.79 as the steady state fluid height, whereas our linearized version is 3.55. And so we're able to see here within the dynamics of what we're doing here, the non-linear and the much quicker one to just code out does in fact give us a more accurate model, but the non-linear, or so the linear model, is going to come into play in a lot of handy ways as we move forward. And so we wanted to be able to show how do we arrive at the steady state conditions, and then how much do they differ from one another. All right, thank you. Next, we're going to move on to part 2.